Okay, hello guys, how are you? Okay, we have, hey, hello guys. So we have 24 of you. Let's just give it one more minute and then we can start today's lecture. Let's see. In the meantime, I'm going to open the, see. Okay. Okay, minute has passed. So let's get this started. Okay, so last time we talked about reflection and transmission of ultrasonic waves. No, what am I doing? Here, okay. So we talked about reflection and transmission of ultrasonic waves. And now we are going to cover a couple of pieces of material, right? The first one is going to motivate how ultrasonic imaging works, right? And this is something that, in principle, maybe we're going to cover last lecture, but it was really planned for this one. So you already had this material on the Paideia site, and then there's a new material that I have uploaded a few minutes ago.
Teacher,
yes.
sorry to interrupt you. The last material you uploaded it's in Spanish, I think. Is that correct?
Which one? Which one? Let me see.
Lecture 6.
Oh, the lecture 6. Yes, that one is in Spanish.
Okay.
Thank you. Okay. Okay. So I'll go back to, no, it's not this one. Is this one. I know it's kind of shocking to be seeing things in Spanish, right? So let's talk about ultrasonic imaging. And so now we're going to bring this back, away from the gray area of waves, and things that, I mean, it's basically a description of physics back to what engineers do on instrumentation. So we should start with ultrasound transducers, right? And first, the idea is a transducer is a device that can generate electrical energy, or sorry, can transform or convert electrical energy into mechanical vibrations and vice versa. It's like a microphone for recording and a speaker, right, for sound generation, both at the same time. Like technically speaking, transducer just means that you can, convert one type of energy into another. Ultrasound transducers actually allow you to do this both ways. And of course, there are other devices for other types of energy that would allow you to do it both ways too. The most commonly encountered transducers that you will find in the market by far, probably all of them, operate based on the piezoelectric principle. And this type of materials, the piezoelectric materials, have been formally discovered by the Curie brothers back in the 1880s. And have been used in ultrasound, since the beginning of the 1900s, actually. So this is a very long, history of, a very, very long history of materials being used for the production of sound. Now, that being said, you can find newer technologies in the market, like CMAT transducers, which are capacitive micro-machine transducers. These ones operate under a completely different principle, okay? And this will not be covered in class. I'm just letting you know those exist. In paper, CMOS transducers have a better performance compared to their piezoelectric counterparts. In practice, I mean, I don't know, it's actually questionable how much better they perform, but still, it's another way that sound can be generated, ultrasound, I should say. Piezoelectricity is relatively simple, right? I mean, is you have basically a material, and when you apply, for example, an electrical current to the material, it will contract, and then you apply a current of a different polarity, and it will expand. So if you do this in an alternating fashion, then you have the material vibrating. And conversely, right, when the material is compressed, there is a voltage potential that is produced across the surfaces of the material. But then when you expand it, you have a voltage that's been reduced, right? So you increase and reduce and increase and reduce. Again, you alternate the compression and the expansion, and that also gives you, like some sort of a sinusoidal, let's say, electric voltage waveform. So it's relatively simple to understand. The first materials were basically crystals, which are okay, but there's only so much that you can actually do with crystals, in the way that you can machine them, in the way that you can cut them. So starting in the 1940s, people started to work on ceramic materials, and this would lead to actually PCT ceramic transducers, which are the lead zirconate titanate compound, which are the transducers that actually dominate the market for better performance, even nowadays, probably. Again, CMOS transducers would probably be cutting very close or even outperforming this technology, but they are not so widely available anyway. Basically, an ultrasound transducer is a device that is built centered around a piezoelectric element, right? For the simplified discussion, again, something similar will happen when we talk about X-rays, for example. We will talk about the anode and the cathode, and those are the key elements, but there's a whole bunch of other things that need to be put together so that the transducer can operate as such. The X-ray tube can operate as such, and the same thing here for the transducer. So what we can observe in the image, let me just grab my board just for 1 second. But what you can observe in here is that you have the piezoelectric element, which is in here, right? And notice how this piezoelectric element is curved, actually, right? It's not a flat membrane, it's curved. And today, during today's lecture, we're going to actually figure out and analyze why is it that it looks curved. But that's not everything that takes place inside the transducer, which the transducer itself it's this, right? Oops. Okay, so horrible drawing skills, but you kind of get the point. That would be the transducer. This thing over here is just showing you that the transducer produces an acoustic beam, right, or a pressure beam that we will talk about the concept of this is focused, right, or it actually becomes relatively narrow. That's the idea of focusing, right, at some depth, with some depth of field. That is, there's a range of depths for which the acoustic pressure beam stays relatively narrow, and then away from it, it diverges both towards the transducer and away from the transducer, like in here and in here, right? So we only care about this region over here for imaging, and that is produced by, again, the transducer. And this is a single element transducer, which is something that you probably wouldn't use for medical imaging anyway. We're going to talk later in the session today what exactly is it that you would use for medical imaging, but to motivate the description, these basic concepts will remain the same. Together with the piezoelectric element, we have at least 2 more elements that become relevant. The first one is the backing material, which goes behind the piezoelectric element. And the second one is the lambda/4 matching layer, which goes in front of the transducer. Okay, there's a electrical matching and tuning, but that goes into any electrical device that needs to be connected, to, in this case, a pulsar receiver for the generation of the acoustic waves, but some other electrical device, right? You always have to do matching and tuning. So let's talk about, the relevant elements that probably you don't exactly know how they work or why they're there, which are the backing and the matching layer. The piezoelectric we already talked about, right? And it's, again, the active element. And then again, just like we described before, you apply electric currents or a voltage in between the back and the front of the piezoelectric material, and you apply an alternating voltage, and you will have a vibration of the device. And this will actually give you an output that resonates at this particular resonance frequency, which is shown in here. The resonant frequency is equal to the sound speed inside the piezoelectric material divided by 2 times the thickness of the piezoelectric material. Okay, and the reason for that is just like it's shown in here in the drawing, right? You have your piezo material, and this will have, some sound speed. And let's say that this, just to simplify matters, right? We have this wall over here that is vibrating, right? So this will actually generate a wave that goes to the back, and then there's a wave that comes, to the front like this. So this is actually, right? I mean, the wave is going all the way to the back, then it's coming to the front, and that's going to create a second wave that comes out, and a second wave that goes to the back, right? And then it comes to the front, and then there's a third wave that comes out, right? And so on and so forth, and so on and so forth, right? So this just happens, or follows from the discussion that we were having during the last lecture, right? There's reflection and transmission of sound. So you have this vibration, right, that's generating, some sort of a wave, and then it's going to be bouncing back and forth in between, the thickness of the transducer material. Because, again, we're simplifying the analysis for the case of a harmonic vibration, right? A vibration that happens at a single frequency. What we're going to have then for each one of these, signals in here, it's sinusoidals, there will be another sinusoidal, here there will be another sinusoidal. In order for those, reflections 1 and 2 and 3 and so on and so forth, to constructively interfere with the first wave that was transmitted, right? The one in here, let's call it 0, right? In order for all of these guys to constructively interfere, you need them to be completely in phase, right? That is, you need that the phase that's accumulated going all the way to the end and then coming back is equal to 1 period of the oscillating frequency, right? Because if it's equal to 1 period, then you know that the things are going to be in phase, like all of those, multiple reflections are going to be in phase, and they are going to make the output signal resonate. That is, each one of the new reflections that comes is going to add to the total power that is transmitted. Okay? So what you need is that the time that it takes to travel is equal to 1 period, which is 1 over f naught, right? 1 over frequency is the period. And that has to be the time that it takes for, the wave to go to the back of the piezo and then to the front, which is equal to what? That time is equal to 2 times the thickness of the piezo, right? Because it has to go all the way to the back and then all the way to the front. So that's 2 times the thickness divided by the sound speed of the piezo, and that gives you a time, right? It's like time times sound speed is equal to propagation distance. And from here, you can directly bring it home to this, right? So that's how you can, relatively easily argue what the resonant condition is for a piezoelectric operating in longitudinal vibration mode, okay? And I guess the bottom line message from this is that once you have a material and the material has a certain sound speed, I'm talking the material, the piezoelectric material, right? You have to play with the thickness of the piezo in order to change the natural resonant frequency of the transducer, okay? Now, the thing about that is just really think about it, right? This means that technically speaking, right, the transducer is going to generate waves that have a very large amplitude for one particular frequency, and then away from that frequency, it's going to generate relatively weaker waves, right? That's the idea of resonance. You have a very large response for one frequency, and then for the other ones, you get really weak responses. And why does that happen? Again, what we said was, if we have a material, right, that, I mean, we're assuming over here there is air, for example, right? I mean, there's nothing, and then everything is coupled going into the medium here, right? That's what would happen if you have a piezoelectric material and you push it, on its own against tissues, right? And that's what would happen. You will have tissues in here, so things propagate into the tissues in the back. You will have air, so nothing goes from the piezoelectric material into the air. Everything stays trapped inside. Now, what happens is that in practice, you don't want that. You don't want the transducer to transmit just one frequency. The reason for that is that transmitting just one frequency gives you a very long signal. And for ultrasonic imaging, what you want is really short pulses. So you need the output signal to have a broad bandwidth, right? Remember that from maybe your early courses in signal analysis or signal processing, depending on your background. You know that the wider the bandwidth, the shorter the signal that you are going to generate. So we have one question in here. So is this all happening inside the piezoelectric? So by all of this, I presume that you're referring to this, right? To these multiple reflections, like going back and then forth and back and forth and back and forth and back and forth. Yes, this would be like the piezo, right? Piezoelectric element. That thing that's bounded by the brackets that I just draw. So over here, you will have, like tissues. And over here, you would have, I mean, the way that we're describing it right now, you will have air, right? Like that's what would happen if you just were to grab the piezoelectric element in isolation. Sure, no problem. So what we do in practice is we don't put air. What we do is we place another material in here, which we call the backing material, right? And the reason for the backing material, imagine the case where, the impedance of the backing material is exactly equal to the impedance of the piezoelectric element, right? And this is a piezoelectric element with, like some impedance. What would happen if I were to actually get my hands onto a backing material that has exactly the same impedance as the transducer, or the piezoelectric, I should say? What would happen? Who wants to participate?
The sound would just pass over following the same direction.
Sorry, again, please.
The sound would just pass along following its direction.
So you're saying that, like, I'm trying to follow, but what you're saying is that, like, when this, like, again, we have something coming out, then we have something going to the back, and what's going to happen to this wave that goes into the back?
It would just pass along, like if there was no barrier.
So there is going to be no reflection over here, right? And that will happen again because remember on that last lecture we said there's a reflection coefficient, which is, you know, difference in impedances divided by the sum of the impedances. So if the two impedances are the same, then nothing is reflected. Everything is transmitted, right? So if we were to have that, which actually makes a lot of sense, right? Because it's like saying it's the same material, right? So if it's the same material, then just things keep propagating. But what happens is that the vacuum material, like imagine, like regardless of how you match it, it typically has a very high attenuation coefficient. So what happens is that, you know, like at some point the vacuum material is going to end, right? And at that point where the vacuum material ends, you would have, right, reflections coming back. But if you make the attenuation coefficient high, then the backing material actually eats away all the signal that propagates from the piezo into the backing material. It dissipates it in this form of heat, for example. So the only thing that comes out of the piezoelectric would be the first signal, and that's it. First signal out, then this comes back, but you know, everything goes into the backing and it dissipates, so nothing comes back out again. If that were to happen, then hopefully you can easily see that every frequency would be transmitted with the same amplitude. Because regardless of the frequencies, right? I mean, there are no multiple waves that combine at the output of the piezoelectric, right? There is just one wave. The other one is completely dissipated into the vacuum material. So the transducer would have that weird ability of producing every frequency with the same strength. The problem of having that is that because everything that goes to the back gets dissipated in the vacuum material, the amount of energy that is transmitted is very weak too, right? Because a lot of the energy is absorbed in the vacuum material anyway. If you actually were to match the vacuum material the way that we're describing it right now, it would produce a very broad output signal, but that signal would have a very low amplitude. Whereas if you place a vacuum material that's equal to air, you know, or something else like that, you would have a signal that's is completely mismatched with the piezoelectric in terms of impedances. You would have a very large output signal, but a very narrow bandwidth. So in practice, what you want is a little bit of the two. So you would design your vacuum material such that you have, you know, a reasonable bandwidth and a reasonable amount of energy that's being produced by the piezoelectric or the transducer, I guess we can say safely in this case, because, you know, we're actually building a compound on top of the piezoelectric element. Okay, so that's one of the things that needs to happen in here. The other element was the impedance matching layer. And this one is very interesting because technically speaking, the matching layer would be, you know, the solution to a relatively, it's not a horribly complex, but relatively complex homework problem, right, for the course, which basically it's saying, like we have, you know, like one medium, right? And let's assume that that medium is, you know, the piezoelectric. And then we have a different medium, which is the tissues, right? Whatever, some tissues. And we want to go from here all the way to here, right? And yes, we can put the gel couplant that we discussed in the previous lecture, right? Super important, we need it. But if we do something like that anyway, right? We are transmitting ultrasound from the piezoelectric, which has one impedance, into the tissues that have a different impedance. And as such, right, it's the same thing. Part of the energy is going to go back into the transducer, only part of it is going to go into the tissues. How do we solve this? We actually place a layer of material in between the two. And again, this is something that you could potentially solve in a relatively complicated homework problem, because you can idealize this as solving, instead of, you remember we saw pressure incident, pressure reflected, and pressure transmitted when we had, one interface in between two media. Well, what if I place a second in here? So we have some transmitted, right? Transmitted one or something. And then we will have a transmitted in here, right? And in here, we will have, this will act, as an incident one. And then we have a reflected one, let's call it internal or something like that, right? So you can actually look at those things, right? And you can realize that instead of having two unknowns, which are, the reflection coefficient for PR and the transmission for PT, now we also have, the reflection and the transmission coefficients for the ones inside the layer, right? Because we have PR, PTI, PRI, and PT, right? So we have 4 unknowns, and we have 2 layers, and we can apply boundary conditions in those 2 layers, right? We have continuity of pressure and continuity of normal particle velocity. Each one of those gives us 2 equations, and we have 2 layers, so we have 4 equations in total for 4 unknowns, and bingo, right? We can actually solve it. I'm not saying necessarily that you want to do it, but you could. And you would get to, some expression that's relatively awful, but not incredibly unmanageable. And once you get to that equation, right, if you were to do it, then the natural question that arises would be, how can I make it so that the transmission coefficient that relates the incident pressure in here to the transmitted pressure in here is equal to 1? What are the conditions that are needed such that I achieve a perfect transmission? Like PR is equal to 0, PRI is equal to 0, and everything just, keeps going through. You do it actually by imposing 2 conditions. You make the width of the layer, right? This thickness of the layer, you make it equal to lambda divided by 4. And the second one is that the impedance of the layer cannot be anything. It has to be something very specific. And the something very specific is this. The impedance of the matching layer has to be the geometrical average of the impedances of the piezoelectric and the tissues. Now, that condition itself, the impedance of the matching layer, fine, right? I mean, with sufficient handling of the materials, right? People have devised ways of, modifying the impedance of the layers or the material that will make the layer. The tricky part is the thickness, because by definition, the thickness is equal to the quarter part of a wavelength, but the wavelength is equal to the sound speed divided by the frequency, which means that technically speaking, right, the lambda over 4 matching layer only allows 1 frequency to be perfectly transmitted across the layer. So in practice, what you would have is several layers that are used to have a better transmitted bandwidth. Or actually, you will build the layer in a fancier way than just, grouping together 1 lambda over 4 layer after another, because that in itself would actually be fairly, fairly unpractical after a little while. But it suffices just to show you some of the challenges that are present in transducer manufacturing and to motivate the need for having both the backing material and the matching layer for, you know, just instead of just having a piezoelectric element just resonating and probably giving you nothing very useful. Questions up to this point?
So in the end, by using the matching layer and the backing material, we can ensure that the most of the frequencies are covered when reading the signal.
Correct. What you actually do is you improve the transmitted power and the bandwidth of the pulse that you're generating. Right? So you try to balance both of those things. Correct. Like in the absence of those two elements, it would just be the piezoelectric resonating very narrowly at some resonant frequency and transmitting very poorly whatever it is that's generating into the tissues.
Thanks, teacher.
Sure, no problem. And once we have a properly designed transducer, the principle of operation of ultrasonic imaging has to do with what's called the pulse echo principle, right? And we talked about it in our first lecture when we dealt with, you know, fundamentals of signal processing and stuff and mathematical background. We have a reflector, right, or some structure that would reflect ultrasound, and now we know that that happens at interfaces or boundaries or layers, you know. But for ultrasonic imaging, it occurs, you know, at a fancier level that we're going to talk about in literally just a minute. But we have some reflector, and the reflector is located at some depth, d. The transducer will send the waves, and the wave will travel all the way to the reflector, and then from the reflector all the way back to the transducer. So the total distance that the ultrasonic wave travels is twice the distance, twice the depth of the reflector. And then if we want to transform that into a travel time, or the time that it takes for the echo to go back, that would be 2 times the distance divided by the sound speed. And that would be the principle that allows us to determine the depth at which the echoes are located, right? In principle, we get this signal, like we get some signal like the one that's been displayed in here, and we see a reflection happening at some time, and then we can transform the time axis into a depth axis, right? We can map this out to an actual depth by assuming that there is a constant sound speed, right? That's a big assumption, actually, because we know that, again, if you're doing abdominal imaging, for example, you know that the fat has a different sound speed than the muscle, which has a different sound speed than the one in the liver, for example. So again, that's a gross oversimplification, but it's one that is used in practice anyway. So you transform the arrival times of the echoes into depths of the structures, and you can display those echoes into an image. In order to display the signal, though, you have to be mindful of a few details here and there. The first one is that remember that the ultrasonic signals are oscillatory in nature, right? So this would be, you know, a very cartoonish signal, right? The blue one, where you see that we have oscillations that are roughly, you know, 1, 2, maybe like 3 periods of the signal, right? Or something like that, or 4 periods of the signal, right? And it has a certain duration, right? This would be an AM, FM signal or something like that, or, you know, an amplitude modulated signal for sure. In the sense that we have an oscillation and then we have a modulation in amplitude, right? Because, I mean, it's larger and then it, you know, it goes down in amplitude on the sides. If we were to display the amplitude of the actual measured signal, which is the blue signal, right? You would see that we have portions of the signal that have very high amplitudes and portions of the signal that have very low amplitudes, right? The points at 0, for example. like in here and in here and in here and in here and so on and so forth. So if I were to directly plot or directly create an image of the amplitude of this, then I would have, very bright spots, which are the ones of the high amplitudes, and then very low amplitude spots, right? Where, you will have blacks in your image. And even though, even if there is just one reflector that reflects the ultrasound, let's say very strongly, that would still produce, regions in the image where I have high amplitudes and low amplitudes, and I don't want that. What I want is something that roughly tells me how strong the reflection produced is. And the only way to do that is to remove the oscillations in the signal. And in order to remove the oscillations, we calculate the envelope of the signal. There are many ways to calculate the envelope of the signals. The one that is more commonly used probably is to calculate the analytical signal, which by definition is equal to this real signal plus J times the Hilbert transform of the real signal. And hopefully you have seen some of these things back in your signal processing courses. Basically, what it says is that if I have a real signal will have a spectrum that has two copies, like the positive and negative frequencies have the same spectrum, the only difference being the phase, right? One is the complex conjugate of the other. That would be a direct consequence of the signal being real. It has to happen that way. So the analytic signal, what it does is it actually completely negate this, right? It will give you a signal whose Fourier transform only has the positive frequencies. Everything else is set to 0. So it will give you a complex signal, right? Because in order for the spectrum to be asymmetric, the signal has to be complex. That you already know. And you can see it in the very definition of the formula, right? If it's xt plus j times the Hilbert transform of x, then that actually means that we're dealing with a complex signal, right? If we take the magnitude of the complex signal, we will actually get the green curve that you see in there, which is the envelope, is the amplitude modulating component, okay? And there are many, many ways that, again, this can be done in practice, calculating the envelope. You could computationally calculate the Hilbert transform, of course, or you can actually do a demodulation. You could have, this analytic signal calculated indirectly and then demodulate it back to baseband, right? Center it around 0 hertz. And, you can do that with IQ demodulation, which you have probably heard, right, before, which involves multiplying the real signal with sines and cosines and mixing them accordingly. Maybe you have read about this. If you have not, then I guess you can look it up. But there are many ways that this can be done, right? Bottom line is you care about finding that green signal, because that green signal will tell you how strong the echo is without, the nuance of having those nulls and peaks that would produce oscillations in your resulting image. And this is what, the process of constructing an echographic image would look like. You have one transducer, right? And you have to make sure that your transducer, which is depicted in here, transmits an ultrasonic beam that's very, very, very narrow laterally. So what you do is you place a transducer with a very narrow beam on top of a medium that you want to create an image of. And then you place it in one location and you produce a transmission. In this case, these black circles, or I don't know if circles, but as much as in the image, represent structures that would reflect sound back to the transducer, right? And then there's a white circle at the center, right, where there are no black smudges. That means that nothing is reflecting ultrasound coming from inside that circle. So you place your transducer, in this case, it's located on top of the diameter or the wider diameter of the circle. And what you see is that you would get the signal that's shown underneath, right? Some oscillations and nothing, because there are no reflectors inside that circle, and then oscillations again. What you do is you take the envelope of the signal, right? So you're getting the envelope. You compress the envelope logarithmically, right? We talked about that before. In order to see the full dynamic range, right? Or to better exploit the dynamic range of amplitudes in the signals, you transform this from linear to decibel scale. And then you map it as the values of brightness in a column of an image. Larger values of amplitude in the reflections are mapped to whiter shades of gray, and lower values are mapped to blacker or darker shades of gray. Okay, so for example, there is that region where there are no reflectors, so there is no signal at the center. That would be completely pitch black, right? Because there's nothing, so that's the lowest amount of energy in all the image. And that's completely black. And there are some regions where the amplitude of the reflections are the largest, and those are displayed as white. And notice, right, how as a result the image has a texture to it. There are some regions in the image where there are white specks, and then others where you have dark specks, like in here and in here. Right, and you have things being bright and then dark and then bright and then black, black again, and that is called speckle. Speckle is one important characteristic of ultrasound images. I mean, it just happens. There is no way that you cannot have speckle in ultrasound images. Okay, so it's there and it's there to stay. In practice, what do you guys think in tissues that are going to be the equivalent of those black smudges in this cartoon that we have over here? In practice.
Lipids.
Sorry?
Fats, lipids. Maybe.
Sure, it could be. So if I have muscle, for example, or a like perfectly lean muscle, I wouldn't get any reflections. I would, right?
Well, yeah.
So what do you think are going to be the structures that are going to produce that? It's a very tricky question because it's very difficult. Sorry, go for it.
More fibrous mass, perhaps.
It's a very tricky question because I guess the correct answer is nobody knows. We know that it has to do with tissue microstructure. Okay, and there's a really old book back from the early 1980s, I think, by Jim Greenleaf from the Mayo Clinic that talks about these things in detail. We know that, for example, if we have the interface in between, like subcutaneous fat and muscle, then there would be a reflection, right? There's two different types of tissues. Then going from, the transabdominal fat into the liver, for example, then you would have yet another interface and you would have some reflections. But if you continuously propagate into the liver, for example, something still, creates echoes that go back to the transducer. And you can actually, you can actually see this texture, right? And people really scratch their heads trying to figure out, what is it the structures are? And the answers change a lot depending on the organ that you're looking at and the types of tissues that you're looking at. Like if you're in muscle, for example, you have your muscle fibers, right? And those are usually packed in bundles, for example. And it's pretty much widely accepted that it's the fascia, right, that surround those bundles, the ones that are mainly responsible for the most significant reflections that you get from muscle. But if you go to the liver, for example, right, I mean, that makes it trickier. Because in the liver, you have something that's more homogeneous, and I guess a homogeneous anisotropic medium, right? As opposed to, again, the muscle or the kidney, right? Where you actually have structures that have directivity, right? In the liver, you don't. The liver is like a sponge, right? And a lot of people were hypothesizing for a really long time that, I mean, if that's what it is, it's like a sponge, then the only thing that could be producing the reflections would be the cells that conform the liver parenchyma. And apparently that's what it is. But more interestingly, at some point, some researchers did some experiments where they denatured, selectively denatured the cells from, liver samples. And it is only when they got rid of the cell nuclei that, the ultrasound signal became significantly weaker. So it was not actually like, quote, the cells themselves. It apparently was tied more to the nuclei of the cells that were related to, the structures that apparently were producing the strongest amount of ultrasound reflections. In the thyroid, you have follicles, for example, and colloids. It's just you have depositories or blocks of colloid material, and you have follicles, and you have aggregates in general, right? And apparently it's these aggregates, the ones that are mainly responsible for the reflection of ultrasound. So it's a very, very, like, in general, it's a very complicated question to ask. But in most of the cases, if not in all of them, it has to do with the architecture of tissue microstructure. So that's something to keep in mind. If it was not for that, right? If there were no microstructures in the tissues that would continuously reflect ultrasound, you would only get reflections at the boundaries in between different organs. And if that were to be the case, then ultrasound images would look significantly different than the ones that we actually see now in clinical practice. So we have a question in the chat, and we have somebody raising his hand. So it's caused by the microstructures of tissues rather than the macro, correct? Again, the macro, like the boundaries in between organs, are going to create reflections too. But the speckle that you keep observing is actually tied to the microstructure of tissues rather than the macro. So that's correct. Breno, I think you were raising your hand.
Yes, teacher. My question is that, so if the microstructure makes, that kind of deviates the direction of the sounds, it would mean that it won't ever return to the transducer. So we would have like black spots.
Sorry, something about changing the direction of ultrasound. That part confused me a little bit.
Yeah, like I imagine if the wave has a specific direction, like transversal, and for example, it starts to hit different microstructure that change the direction of the echoes, or I don't know how to express it. Maybe the echoes get trapped inside the organ and they never return to the transducer.
No, actually that really doesn't happen. It doesn't happen because, again, the scattering occurs at very low contrasts, right? So, and it also tends to happen that the scattering occurs from structures that are very, very small compared to a wavelength. When that happens, like if there is one reflector in here, like this guy, right? It's going to produce reflections that are omnidirectional, right? So it's going to act like a point source. which remember we talked about that when we talked about the spherical waves, right? So it's going to be picked up by the transducer anyway. And it's going to be picked up by the transducer, of course, you know, when the transducer is landing on top of it, right? But it is still going to, like, it's going to do something like that. So that's just something to keep in mind.
Teacher,
Yes.
is there a chance that the speckles are caused by blood flow or any other liquid flow?
They could also, you know. Like, I mean, do blood clots produce reflections of sound? Yes, they do. But, you know, like, again, right now we're talking about, you know, reflections from structures that happen at a micrometer level, right? Which that's the other defining behavior of speckle. Speckle occurs when you have many scatterers within a resolution cell of the transducer. The resolution cell of the transducer, spoiler, you know, because that's something that we still have to talk about. It's in the order of maybe, you know, like tens or like several tens of micrometers, you know, in every direction probably. So you're looking at structures that have to be several structures that are smaller than that, right? And those are typically tied to cells. Anything bigger than that, you could probably observe it directly into the image. It would be, you know, above the resolution capabilities of echographic imaging, so you could see it. For example, there are vascularities into the liver, right? The vascular tree. Typically, you know, most branches, you will see them. I mean, of course, our branches are huge, but even small branches, you will be able to see them anyway, right? Like a tiny black spot in your image, but you will be able to see it. So the speckle is more linked to very, very microscopical things. And again, it really, really depends, right? The speckle texture, again, it's related to the size of the resolution cell, which in turn is related to the wavelength of the ultrasonic wave. So if you go to higher frequencies, the speckle looks different than the one that you have when you're at lower frequencies, for example. So those are different things to come, you know, that come to mind. And of course, the speckle pattern will again change, you know, depending on the wavelength, which structures are, you know, like small compared to that wavelength or not. So even that is frequency dependent too. Do we have any other questions?
Yes, teacher. About how does this work? I understand that the ultrasound transducer is like emitting a pulse, like a Dirac delta function, right? It's one pulse or not?
No, I mean, it doesn't transmit a direct Dirac delta. It transmits, like in practice, it will transmit something that, I don't know, looks something like this, right? I mean, some short sinusoidal oscillation. Because remember, the transducer is an oscillating, it's a resonator, right? With a bandwidth. So it will produce something that looks like a short sinusoidal burst. Carry on, please.
Oh, so like a wavelet, but like
Sure.
continuously in a periodic like behavior, like that?
Roughly, right. I mean, again, I mean, it's probably, yeah, something like, yeah, exactly, like a short sinusoidal burst. Right.
Okay, and what it gets when it sends the environment or the medium is what is showed there in the signal in the right down corner.
So in
Lower
panel
corner.
B, like this?
Yeah.
Correct. I mean,
So
you will get some echoes, right? I mean, there are structures like those black circles are generating echoes, and, you know, several of them, there are several echoes, and they're being sensed by the transducer, and the echoes overlap on top of each other, right? It's not like you get one echo different from a second echo. Like, you have several echoes landing on top of one another, and, you know, that's why you have the speckle. But yeah.
okay, so the envelope function like works to determine where are the peaks of this.
Not the peaks really, but I mean the envelope, what it does is it removes the oscillatory behavior. The ultrasound transducer again will oscillate because that's just what it does. But you know, displaying the amplitude of an oscillatory signal would, you know, give you horrible variations. You know, the variance of the signal would be horrific. Because, you know, again, you know, you can have a strong reflection or a weak reflection, but in both cases, right, of a strong and weak reflection, you have portions that have very low values, the points of the oscillation where the voltage goes near zero. So if you're to display that linearly, then you have, it's not very intuitive to look at. It's much more intuitive if you look at the envelope, because then, you know, you have regions where the echoes are strong and those have large amplitudes. And then when echoes are weak, you have very low amplitudes, but you don't have low amplitudes because the signal is oscillating. That's the reason why.
Okay, so what we're watching in the image of the V mode image is like a 2D graphic of all the envelopes with the width of the tiny transducer, sorry, tiny piezoelectric that is used, right? Or something like that.
So again, right, I mean, when you place a piezoelectric in one location, you get one echo, right? Like one set of echoes, I should say, like one panel B. And then you take the envelope, you calculate the logarithm. So you make this into a logarithmic scale or a decibel scale. And then you bring that into one column of the image. Then you move the transducer to a second location and you repeat the process. And the same thing in a third location and a fourth location and so on and so forth. So for every location that you're using, right, you have a new set of echoes that will in turn become a new column in that V mode image, right? And that's how you construct the image, by moving the transducer, in principle. Like again, in practice, you're not going to move anything because that will be completely impractical. But in principle, that's how it would be done.
Okay, thank you.
Sure, no problem. Let me see. So I think, yeah, this is the last one, so we can take a break because we have our first quiz today. So we're really excited about that. So for the spatial resolution, right? And that's one of the things that, you know, we talked about also, or I think it was in the material for the, no, I think it was in the material for the class or the lecture that we didn't have, unfortunately. The spatial resolution, right? It basically tells you how close can two structures be in an image before you lose your ability to determine that there are two structures rather than one, right? And V mode imaging is an imaging modality where the spatial resolution is anisotropic, unlike, you know, other imaging modalities. Meaning that you have a different resolution in the axial direction, which by the way, this is axial and this is lateral, okay? In the axial direction, the resolution depends on the bandwidth of the system. These are rules of thumb, but technically speaking, it's equal to the pulse duration. So again, if we have a transmitted signal, right, that has some duration, and we can call this tau or something, right? It would be equal to C multiplied by tau divided by 2. And that would be the axial resolution of the system, which is basically what happens when you convert the whole duration of the pulse into a distance, right? Because remember that the way that we do this is we determine that the depth is going to be equal to sound speed multiplied by time divided by 2. And the divided by 2 comes from the fact that we're operating in pulse echo. So the times that we're measuring are, you know, going to the structure and then from the structure to the transducer. So in order to reduce that into distances, we have to divide by a factor of 2. So actually, if the pulse has a duration of tau, then the axial resolution would be c times tau divided by 2. How do you want to define that duration? Well, that's a different issue, right? That's up to you. Oh, there's somebody waiting to be admitted. Okay. And then we have the lateral resolution, which depends on the ultrasonic beam width. Okay. What is the beam width? It's the width of that red thing that I just showed in there, right? And hopefully that makes sense, right? I mean, if you have a transducer that produces a pressure field that is mainly limited to that very narrow red region over there, then of course, when the transducer is sitting in here, right, it's not going to get signal from, let's say, here, right, that X over there, because it only sees things that fall within that red spot, or sorry, that red fringe. It doesn't sense things that are outside of it. So that X is invisible to the transducer. But if I have a transducer that somehow now, has a very broad beam like this, and let's say that, again, I maybe have some reflector in here, it would sense it, right? So you want to have the narrowest beam possible. And we will actually see in a very little bit that the beam width of a transducer, that the ones that we're going to use in practice are actually defined by a property that's called the focal number. And we will see later on what the focal number is. So it's the focal number multiplying the wavelength. So both the axial resolution and the lateral resolution in principle are, some multiples of the ultrasonic wavelength. Which means that technically speaking, the higher you go in frequency, the better the resolution of your system. You would be able to look at smaller structures if you go to higher frequencies. Higher frequencies, then better resolution. So the question from me to you would be, why is it then that we don't use 100 megahertz for ultrasonic imaging for everything, or 1 gigahertz?
Due to attenuation?
Correct, due to attenuation. Attenuation increases monotonically for increasing frequencies for every tissue or every material that we're aware of. So if you go to higher frequencies, right, those are going to be attenuated faster. Actually, typically it's exponentially faster. So you actually want to have a frequency that's high enough that it won't be completely attenuated by the medium. And that would depend on the clinical application you're looking at. If you want to do abdominal imaging, the abdomen is a very thick portion of your body. If you want to go all the way inside the liver, for example, it could be several centimeters. And the liver is very, very big. So you want to be able to look at the whole thing laterally too. So for that, you're going to use very low frequencies. If you want to look at the thyroid glands, for example, you would want to use very high frequencies, right? And that's not as deep as, going inside the liver. So you could safely do that. Okay. So, I mean, again, those are just points of consideration to take into account in here. Any questions up to this point? Okay, so let's take only 5 minutes, and then we are returning here so we can continue with the discussion and we can have our first quiz.
Teacher,
Take
there's
5
a
guys.
question in the chat.
Oh, there's a question in the chat. Let me see.
Yes, from Emilio.
Is that the reason of the shape of the transducers? Which one, Emilio? Can you elaborate a little bit more, please?
Yes, teacher. I mean, there is a type of transducer for like Apache cases, or for example, to tuber cases. or for wrist cases. I see a lot of shapes from transducers in every type of echographic mode. So that is my question, I think.
Oh, okay, sure, I understand. We're going to talk about the types of transducers that you can find in clinical practice later on in the course. There's mainly 3 of them: phased arrays, curvilinear arrays, and linear arrays. So hopefully at that point I can, answer your question. And if not, please feel free next lecture to ask the question again. But we're going to cover that. Don't worry about it.
Okay, thanks.
Sure, no problem. It's the other way around. Okay, guys, let's take 5. Okay, and we come back. Okay, let's carry on. So we have enough time for the first quiz, which was actually, hopefully I did it right into designing one that shouldn't be that much of a problem in terms of the time that it's going to take. Okay, so let's see what we have in here. And let's go to lecture 6. Okay, so let's see. Okay, so let's talk about this. This would be lecture 6 and materials in Spanish. So we'll just have to put up with that, okay? So there's a whole bunch of things to discuss in here. The first one would be, we have been talking about, in general, the wave equation, and then we talked about, the transducers and how they're constructed. But all of this will have to lead up to a concept that's super important for ultrasonic imaging, which is the concept of beam forming. Remember that we said that the transducer will generate waves, within a beam, right? And that's just what it is, right? It's a beam, right? It's a region of space where the ultrasound, has the largest amplitude, or measurable amplitude, of course. And outside of that beam, there would be some ultrasound signal, but it would be super weak. So most of the signals that we're going to receive come from that relatively narrow, hopefully it's a relatively narrow region of space, right? So as we saw, the narrower the beam, the better the image quality that we can get. Okay, so in order to do that, in order to analyze that, we need to develop some building foundation for, how beamforming works. How can we create those beams? And that leads us to analyzing some mathematical models, that are there in your material. So you can actually, like read some of the material in your free time afterwards, analyze it, digest it a little bit, right? And the material starts the discussion with something relatively simple, which is what happens if I have not exactly a point source, okay, but something that is very, very small compared to a wavelength. When something is very, very small compared to a wavelength, right, we still assume that it radiates sound as if it were a point source. The only difference is that that point source has an amplitude of the pressure waves that are being generated, and that amplitude is actually a function of a couple of things, right? We define a radiation force Q, which is equal to the surface area of the radiator multiplied by the particle velocity at the surface of the radiator, right? So let's say that we have a sphere. A sphere will have a surface of 4 pi times radius to the square, right? So we have 4 pi a squared. And then we multiply that by the velocity of the surface. So we call that u naught, for example. Now, the amplitude of a pressure wave is related to that the pressure wave that this vibrator would generate is related to the radiation force Q as this expression over here, right? So basically P would be equal to e to the minus JKR divided by R, right? Which is what a point source would do, but some amplitude, right? And the amplitude is given in here, right? The amplitude is directly proportional to Q, which is nice, right? I mean, we know that if the radiator is very small, right, but still has a larger surface area than some other radiator, then it would radiate ultrasound more effectively. We know that if the radiator has its active surface vibrating with more amplitude, then it would generate a stronger pressure field too. Okay, those things are kind of intuitive. And regardless, you know, you don't need to memorize this by any stretch of the imagination, okay? So what happens though if we have a large ultrasound transducer? If we have a large ultrasound transducer, then tough luck, right? Because that's where our ability to explain this in simple terms goes down the drain. We don't know how to do it. But we know one thing, we know how to mathematically set up, you know, maybe not necessarily come up with an analytical expression for the pressure field, but we know how to set up the analysis of the situation. Because what we can do is we can start to chop this guy into tiny, you know, differential of surface elements, like a lot of them, right? And so on and so forth. Boom, boom, boom. And each one of these differential elements, I make them very, very small. And that's something that, you know, in engineering and science, we do all the time, right? We discretize the surface into differential elements. Like in general, we always can have, you know, a two-dimensional integral, which that's basically what it is, right? We have a differential of surface. And if we have a differential of surface, which is vibrating at some velocity u naught, right? We can define a differential of Q, which is only equal to the differential of surface times the particle velocity at that differential of surface. Based on everything that we said before, then we can have the differential of pressure that's being produced by that tiny piece of the radiator vibrating as the differential of amplitude times e to the minus jkr divided by r, right? And we can relate the differential of A to the differential of Q, and we can relate the differential of Q to the differential of S, right? So the differential of P actually can be related to the differential of surface, right? In the surface of the radiating element times, you know, some constants times the velocity of the differential element times e to the minus jkr divided by r. And if that is the differential of pressure that is produced by some tiny element differential of surface, then we can calculate the whole pressure that's generated by the whole radiator as the integral of the differential of pressures for all the differential of surfaces in the surface of the radiator. So we can actually calculate it like this. Okay. And that's actually very interesting from the point of view that if you guys have a computer, right, you can actually calculate, right, what the pressure field would be produced by a source of an arbitrary geometry in some arbitrary point in space by basically asking MATLAB or any other software to calculate this integral for you. Okay, like in principle, you could. Like in practice, nobody would, you know, because that would be horribly inefficient, but you could, potentially speaking. Okay, now that doesn't help us a lot in the sense that, I mean, more than having a recipe for computationally calculating the pressure field, we are not gaining a lot of insight into anything. And I have already told you guys that my goal in this course is not for you to, be mega proficient analyzing some equations that, like maybe they don't mean anything specific to you, but rather to understand what the equations are trying to tell you and learn how to generalize some lessons learned, into different scenarios and, analyzing and assessing, things that are new to you. So that's the power of math, learning new things, not just rehashing things that people already know. Any questions up to this point? Okay, so I'm assuming no. So we have this horrible equation, right? And so far that horrible equation is really not telling us much. So there's a couple of reasons why, right, in general, you want to use radiators that are not very small compared to a wavelength. The two reasons, the first one would be that the transmitted power would be super small, right? Which hopefully makes sense to you guys, right? I mean, if I have, a speaker that's like super tiny compared to, a kick-ass, subwoofer, that generates a lot of sound and resonates your whole neighborhood, right? It's very clear why, in general, larger radiators are better, right? You have an active surface that's bigger. So you're moving more particles in the air or whichever medium you're generating the mechanical wave. So you generate more sound, right? The second reason is probably equally, if not even more important, which is that if you have very, very small transducers, they would behave like a point source. And point source don't have directivity, meaning, again, if you remember, we said, okay, here's the interface, and then here I place my transducer. But if my transducer is a point, this is generating sound omnidirectionally. So if I actually get a reflection, I cannot say that the reflector was, oh, so it's in this location. God knows, right? Because it could be anywhere. Maybe the reflector was in here, like miles away from the transducer. And I'm still assuming that the reflection comes from underneath the transducer at some very large depth. I really wouldn't know how to locate objects if my transducer wouldn't have directivity. So we really need to have directivity. We really need to have a beam. And for very small sources, the beam doesn't occur. It doesn't exist. It's omnidirectional in propagation. So in order to actually do this, we go to some models, for acoustic radiation. And one of the ones that you would probably more commonly encounter in the literature is a circular piston. A circular piston is actually a very nice model, for it's a very common design for single element transducers. And circular pistons you'll probably very commonly find for non-destructive evaluation of materials. Very rarely, if not any like at any point, for tissue characterization or for ultrasonic imaging of tissues, medical imaging. But you would find it for non-destructive evaluation of materials, okay? And the circular piston is just that. It's a membrane that has the shape of a circle, right? And in this case, that membrane is located in the XY plane and is radiating, into the XYZ region of space, right? And understanding that because this is a circle, then the acoustic pressure field that's been radiating has symmetry, right, along the phi angle, right? So in principle, we have a theta angle and we have a phi angle, right, which is the angle in the XY plane. But again, the radiator is a circle, so it really doesn't matter which plane you use, like a plane, of course, that includes the z-axis. It really doesn't matter which plane you're looking at, the pressure field would be the same. Then this would be, cross-section where we have a lateral distance in here in centimeters, and we have an axial distance here in centimeters too, right? So this would go along the z-axis. and this can be, I don't know, X or Y, for example, it would be irrelevant again because of the circular symmetry of the radiator. And this would be a two-dimensional plot of how the pressure field would look like. So hopefully what you can see here is, there's a region in here that goes something like this, right? Which is, it looks like a rectangle. And then after some point, it starts to diverge like this. So it's like a funnel, right? It's like this, and then eventually it will go like this, right? That's roughly how it goes. What do you think is the diameter of the circular piston? Roughly. What do you think?
1 centimeter.
1 centimeter.
1 centimeter diameter? Why?
Because of the lateral distance.
Because of this distance over here?
Yes.
Okay, so I would probably say this is closer to 0.75 rather than 0.5, right? So probably something about, yeah, maybe 1 to 1.5 centimeters, something like that, right? Exactly. Basically, right, it's the same thing that would happen if you were in a very hot summer day and you would grab a piece of paper, so you can move it back and forth and you can, throw some air into your face. The piston is going to move very efficiently the particles in front of it, right? And that follows logic and intuition. And then eventually, right, as you start to getting farther and farther away from the transducer, eventually, right, this cylinder thing is going to become something that starts to diverge, right? Because you're farther away, and then, particles can actually effectively start moving to the sides, and then everything disperses and dies off eventually, right? And this basically separates two regions, right, roughly speaking, which are the near field and the far field. The near field is the acoustic pressure field that's produced closer to the transducer. And the far field, as the name would imply, is farther away from the transducer. And next lecture, we're going to talk about the properties of the near field and the far field and why those two regions are important for imaging and how we can actually use them eventually for beamforming. Right now, what we're going to do is we're going to stop with the lecture itself, and we're going to start with the quiz, which should be open right now. Can you please check that it's open?
Yes, teacher, it's open.
Fantastic. So the quiz is asking you just one simple question, right? So an ultrasonic device is used for hepatic imaging. What is the amplitude of the reflected wave that is produced when the tissue directly on top of the liver capsule is muscle? And the second scenario is that it's fat. Any questions? Go for it, guys. Best of luck.
Thanks.